Okay, in the last video, we defined the line integral along a curve with a given function, blah, blah, blah. I'm not going to explain all that again. I just wanted to go through one more example here because the question becomes, maybe from a graphical perspective, and here I'm restricted to two colors that actually show up well on this board. We generally have these nice smooth curves C, but what happens if I have this curve and then maybe I have a second curve defined completely differently? Is there a way to get the line integral along the whole curve? And as it turns out, we can do the same trick we do going all the way back to Calc 1. If I call this C1, the first curve up to here, and call this C2, then if I want the line integral of all of C, C is just equal to C1 plus C2. So I just find the line integral along this curve and along this curve and then add them together. Which is, again, no different than Calc 1. Find the area under this curve, find the area under this curve. If it's a piecewise function and the curve jumps around and it's not continuous, you find each individual integral, each individual area, and then add them all together. So the same principle applies here, but I wanted to work through one just so we're all clear on it. So, let's see. Let's see the piecewise smooth curve given by the line segment from 0, 0, 0 to 3, 0, 4, followed by the line segment from 304 to 222. And we will let f of x, y, z equal xz plus y. I want to find the line integral. I'm not going to take the time to graph this. It's just a couple of line segments in free space, not a big deal. But then clearly, all I want to do is maybe let this line segment, I'll call it C1, the first one, and then the second one, I'll just say right here, is C2. And then C, my whole curve, will just be the first line segment plus the second line segment. Which just means to get my line integral, I have to find two separate line integrals and add them together. So let's see first. I need to find the path C1. My parametrization, well, since it's going from 0, 0, 0 to 3, 0, 4, that's not that big of a deal. It's just 3t, 0, 4t, as 0 goes from t to 1. All of you can do that, I know. And I would point out again, this is like the easiest parametrization I could come up with really quickly. And it goes from 0 to 1. As we said in the last video, these line integrals are independent of the parametrization you use, which means if you come up with a different parametrization, as long as it gives you this line segment that you want, and your limits on your t are set correct, then it's completely fine, and you can get your line integral the same. Okay, and then for C2, which we'll just call this R sub 1 and R sub 2 to distinguish them, I get 3 minus t, 2t, and 4 minus 2t, as t also goes from 0 to 1. And again, for this, I'm not taking the time to do all the calculations out for this. All I did was find the line segment from here to here, generate the parametrization, not a big deal. 2 minus 3 is negative 1, 2 minus 0 is 2, and 2 minus 4 is negative 2. And then my starting point was 3, 0, 4, right here. So not a big deal, pretty straightforward parametrization. But now, I just need to set up my line integrals, and yeah, I'm gonna have to do this twice. So let's see. First I'll find my derivatives. So dr sub 1 dt, this one right here, the derivative is equal to 3, 0, 4, which implies the magnitude of the first one is equal to 9, 4, 25. That's 5. I got that one. Good. And then my second derivative for that one is -1 to -2. So then my magnitude would equal 1 plus 4 plus 4. That's 9. That's 3 right there. Good, and everything checks out. Now I need to find f of r of t, but keep in mind I'm going to have to do this twice. So we'll do f of r sub 1 of t, which is just equal to f of r1 of t is 3t, 0, 4t. F is xz plus y, so that will be 3t times 4t, which is 12t squared, plus y, which is 0. So it's 12t squared. And f of r sub 2 of t is f of 3 minus t, 2t, 4 minus 2t, which is, let's see again, xz, which is 12 minus 6t minus 4t, which is minus 10t, plus 2t squared, plus y, which is 2t, and I know I'm just about out of room, but when I get out of the way, I'll be able to see everything. When you simplify it and rearrange it, you get 2t squared minus 8t plus 12. And now I have the pullback of the first curve and the pullback of the second curve. Now I can plug all of that into my line integral and get a solution. And I guess maybe, is this a good black one? It is good. Okay, I'll write it out long form and then maybe avoid the calculations. So this is the downside to being left-handed. It's the integral of, we'll start with C1. So f of r1 of t, which is 12t squared, times the magnitude, which for the first one is 5, dt, as t goes from 0 to 1, plus the integral of the second, which is 2t squared minus 8t plus 12, times the magnitude of the second, which is 3, dt, again as t goes from 0 to 1. And admittedly, you have to do a lot of calculations to first get your parametrizations, then get your derivatives, then your magnitudes, then get the pullbacks, then plug it all into this formula. But that's just all the busy work you do at the beginning, just like on your exam, finding those limits of integration. That's the busy work that's required, because here, this is actually pretty much trivial. Simple power rule, power rule, power rule, power rule, not a big deal at all. All integration you can do. It's the setup that matters. And just in case you care, the first integral is equal to 20, the second one is equal to 26, which makes my total line integral equal to 46. And again, I do actually stress, as I stressed in the last video, all things being equal, we're not actually doing much here. I mean, this is more a review of stuff we've already done. We did this earlier in the semester with my arc length parametrization. We algebraically manipulated our formula to get it in this form, which we called the line integral. And then the rest of this is all just busy algebraic work, a lot of which we have already done before, finding parametrizations, derivatives, and magnitudes, and then doing some algebra to get an answer at the end. But the goal is to use this to then solve more complex problems. This is more the little review stuff we do at the beginning so that we can get to the more complex stuff we want to do next.